Hey guys, Dr. Tim Kruse, exponential growth and decay word problems today. Now, before we get started with the word problems, let's just kind of review exponential growth and decay. So let's say we start with one bacteria and let's say it doubles every hour. All right, so it's obviously growing. All right, if we had one bacteria to start with, and then it doubled, then I would have 2, and then if it doubled again, I'd have 4, and if it doubled again, I'd have 8, and so on. So it's growing. We have more and more bacteria as time goes by. Well, here's what your graph would look like. All right, on the x-axis here, we might call it x, or maybe sometimes we call it t for time. And on your y-axis, sometimes we call it y if we're just using good old x and y. Or instead of y, we might use f of x. Or maybe if I'm talking about the bacteria problem, I'd say, well, the number of bacteria with respect to how much time has gone by. Here's time down here. So all of these could represent y, and x could be replaced by t if you like. All right, so at time 0 here, if I go one step up, that's 0, 1. That means at time 0, I had 1 bacteria. And then 1 hour later, if I go 1 to the right, now I have 2 bacteria. And if I go 2 to the right, now I have 4 bacteria. And after 3 hours, I have 8 bacteria. And after 4 hours, it skyrockets up there to 16 bacteria. So you can see that the y value started with 1, and it doubled to 2, doubled to 4, doubled to 8, and doubled to 16. All right, that's an example of what exponential growth looks like. It looks like something that is very, very close to the x-axis, and then kind of grows slowly, grows a little faster, and then skyrockets. Exponential growth. As time goes by, as we move this way on the x-axis, as time goes by, our growth gets more and more and more, faster and faster and higher and higher. All right, now how do we come up with an equation for this exponential growth example? Let's just look at the ordered pair 4, 16. After 4 hours, I had 16 bacterias. So if I use function notation, f of x, and the x is 4, I would say, well, f of 4 is 16. The function after 4 hours had 16 bacteria. Well, how did I get that 16? I started with 1, and I doubled it, that's 2, and I doubled it again, that's 4, and I doubled it again, that's 8, and I doubled it again, that's 16. That's how I got that 16. Now, a short way of writing repeated multiplication, we're multiplying by 2 over and over and over and over again. We multiplied by 2 4 times. So using an exponent is a short way of writing repeated multiplication. I have 4 of these 2's being multiplied by the 1. So 1 times 2 times 2 times 2 times 2 can also be written as 1 times 2 to the 4th. Now we kind of repeat the pattern down here. What about this 3, 8? After 3 hours, I had 8 bacteria. I could say f of 3 was 8. How did I get the 8? I started with 1 and I doubled it 3 times. So it's 1 times 2 to the 3rd. All right. Exponents are a short way of writing repeated multiplication. What about 2, 4? After 2 hours, there are 4 bacteria. So f of 2 is 4. How did I get 4? I took the 1 and I doubled it twice. So took the 1 and I multiplied it by 2 twice. F of 1 was 2. So it's just 1 times 2. That's 1 times 2 to the 1st power. Now this one's a little tricky. F of 0, my starting value here, f of 0 is 1. Well, that's just 1. There's no real difference. All these up here were multiplied by 2, 2, 2, multiplied by 2, multiplied by 2, multiplied by 2. Well, technically, this one is multiplied by 2 if you raise it to the power of 0. That's a weird property. Anything raised to the power of 0 turns into 1. So 1 times 1 is 1. All right, kind of looks weird right here, but it kind of makes sense here if you follow the pattern of the exponents, 4, 3, 2, 1, and then 0. All right, now let's go ahead and use this information here to write a formula. So f of whatever the x number is, might be 4, might be 3, might be 2, might be 1, might be 0. I can say f of whatever x is, whatever x I choose, f of x is, well, look at how we wrote this every time. Some of these things stayed the same, and some of them changed. The 1 stayed the same all the way down. So 1 goes here. And then I multiplied times 2 every time. Times 2, times 2, times 2, times 2. So that stays the same. So the 1 is the same no matter what x is, and the 2 is the same no matter what x is. But look at the exponent. The exponent changes from 4 to 3 to 2 to 1 to 0. We're saying the exponent varies. That's why we call it a variable. Our variable is the exponent. And if you'll try and match that exponent up to your x number, lots of times they match exactly. So this is 4, so is x. If x is 3, my exponent's 3. If x is 2, my exponent's 2, and so on. So the exponent is just whatever x happens to be at that moment. So I can say f of x is 1, the number of bacteria we started with, times 2, and then the x just tells you how many of those 2's to multiply. All right, so it looks like this, a little cleaner. I can say f of x is 1 times 2 to the x, like this. You know, if I'm talking about bacteria, I could say, or I could write it like this. The number of bacteria after a certain amount of time has passed is 1 times 2 to the t. See where the x is? All right, the exponent goes right there in the parentheses. So if they say use t for your x-axis, well, then this will be a t and that'll be a t. Or they might be talking about maybe the number of deer in a pasture after a certain amount of days. I probably shouldn't use deer, that's got a D in it. Maybe the number of fish in a pond after a certain number of days. So n in terms of d is 1 times 2 to the d. Or maybe you're doing a profit function, and you might say something like the profit kind of depends on how many widgets you produce. So p in terms of w is 1 times 2 raised to the w. All right, this 1 here, that's what we started with. We started with 1 bacteria. What we started with was 1. I always like to put it right after the equal sign there. And the 2, well, that's what we're multiplying by. You know, we multiply times 2 times 2 times 2, however many 2's we need. And this guy up here, that's the exponent, which is your signal that this is an exponential growth formula. It's growing, it's doubling, 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 doubling. It's getting larger and larger and larger. It's growing. And if an exponent tells you how fast it's growing, then it's exponential growth. Now, more formally, this number that we started with here is called the initial value, what you started with, the value you had initially. And then this number here that I call multiplier, the number you're multiplying by, officially it's called the growth factor. Factor is a number that you multiply. So we are multiplying by 2. So instead of multiplier, we're going to use the word factor. And we're going to say growth because it's growing. It's a growth factor. The number that we multiply is making this thing grow. The number that we multiply by is making our initial value grow. All right, exponential decay works in a similar way. Let's say we start with 16 bacteria and half of them die every hour. So they're decaying. We have fewer and fewer bacteria. We'll start with 16, but then if half of them die, an hour later I have 8. And then if half of them die, an hour later I have 4, and so on. So I started with 16. At time equals 0, I had 16 bacteria. An hour later, I only had 8. And then 2 hours later, I only had 4. And 3 hours later, I only had 2. 4 hours later, I only had 1. So I started with 16, and then half of that's 8, half of that's 4, half of that's 2, half of that's 1. So as each hour goes by, I have fewer and fewer bacteria. This is decaying, all right? It's becoming worth less as time goes by. Remember, this is the x-axis. Usually we call it t for time. Just depends on your story problem. This is the y-axis. If I'm using function notation, I'd say it's the number of bacteria as time goes by, or b in terms of t, or b of t. All right, let's talk about how we got these numbers and come up with an equation here. I like to start with the 4 first. So after 4 hours, I was down to 1 bacteria. So f of 4 is 1. Well, how did I get that? I took my initial value. Remember, I started with 16, and I cut it in half. All right. Now, you can do this a couple different ways. You can multiply by 1/2, or you can multiply by 0.5. They're the same thing. So I used both of them just to show you that they're interchangeable. So 16, I took half of it. Multiplying by 0.5 is the same thing as taking half. 16 times half is 8, times half is 4, times half is 2, times half is 1. That's how I got this 1. I took 16 and I halved it 4 times. All right, that's the exponent. I took 16 and I multiplied it by a half 4 times. I halved 16 4 times. Up here I started with 16 and I took half of it 3 times. So I multiplied it by 0.5 3 times. 16 times 0.5 raised to the third power. And the same thing here. I wrote this with 1/2 just to show you it doesn't matter. 16 times a half is 8. 8 times a half is 4. So 16 times a half, or 16 times 0.5 times 0.5. I kind of like the decimal better if it's nice. So 16 times 0.5 twice. 16 times 0.5 once. 16 times 0.5 0 times. All right, we didn't multiply by 0.5 that time. Look at what stays the same and look at what changes. So 16 times 0.5 is the same all the way down. So it's definitely going to be 16. It's definitely going to be times 0.5. The only thing that changes is the exponent. And again, the exponent exactly matches our x. Our x goes inside the parentheses there. So f of x is 16 times a half raised to whatever the x is at that moment. So f of 4, the x is going to be 4. F of 3, the x is going to be 3. So f of x is 16 times 0.5 raised to the x. Lots of different ways to write it, like this. Or if you want to use the letters in the word problem, you'd say the number of bacteria after a certain amount of hours has passed is 16 times a half raised to the number of hours that have passed. Or maybe the number of fish in the pond after a certain number of days is 16, what you started with, times 0.5 raised to the number of days that have gone by. Or if it's a profit formula, the profit after making a certain number of widgets is what you started with times a half raised to the number of widgets that you made. Again, 16 is what you start with. You're multiplying by 0.5 or a half, either way. That's your multiplier. And using an exponent tells you it's an exponential growth or decay equation. This one is decaying. 16 is becoming smaller and smaller and smaller because we're taking half of it every time. Another way to look at it is if you're multiplying by anything less than 1, it's going to make the 16 smaller. 16 times 1 would be 16, but 16 times anything less than 1 will make 16 smaller. All right, and again, 16 is your initial value formally, and using more formal verbiage, 1/2 is, I call it the multiplier, but its official name is the growth factor, the number you're multiplying by. All right, I think we're ready for some word problems. So an amount A, we're just going to call it A for amount, is initially 18. So it starts at 18. To find next year's amount, we multiply this year's amount by 8. Okay? Find a formula that gives the amount A after T years. Okay? So let's just kind of break it down here without drawing a picture or anything. Next year's amount will be this year's amount times whatever we're multiplying by, that's our multiplier, raised to however many years have gone by. Another way of saying it is your ending value is your beginning value. Initial value means beginning value, what you started with, times your growth factor, whatever you're multiplying it by, raised to how much time has gone by, whether that's years or days or months or whatever. All right, that's time. All right, so using their letters, they said the amount A depends on how many years have gone by. So A depends on T. The amount depends on how much time has gone by. So the amount, in terms of how much time has gone by, is what you started with, 18, times what you're multiplying it by, 8, raised to however many years have gone by. And here it is a little bit nicer. A of T is 18 times 8, this many times, whatever x happens to be, whatever T happens to be at that time. So it's always going to start with 18. It's always going to be multiplied by 8 a certain number of times. It just depends how many days or months or years you're letting go by. All right, you guys try a couple here. So an amount, I'll show you all three, and you guys can pause the video and see if you can work these out. All right, an amount A is initially 9. This is number 1. To find next week's amount, we multiply this week's amount by 3. Find a formula that gives the amount A after t weeks. So it's going to be A of t. Number 2, an amount is initially 15. To find next decade's amount, a decade is 10 years. To find the next decade's amount, we multiply this decade by 0.6. Now notice that's less than 1. That's going to make the 15 smaller. Every time you take the 15 and multiply it by 0.6, it's going to get smaller. You can see that on your calculator. Just grab your calculator and do 15 times 0.6 and see what happens. It's going to get smaller. And then if you multiply it by 0.6 again, it's going to get smaller. That's decay. Find a formula that gives the amount A after t decades. So A in terms of t again. And then finally, number 3, an amount is initially 8. To find next week's amount, we divide this week's amount by 9. Find a formula that gives A after t, so A of t again. Now this one uses the word divide. We don't divide in these formulas. We always multiply. So you need to remember that 12 divided by 4, you know that's going to be 3, right? Well, that's the same thing as 12 times 1/4. They're both going to give you the answer 3. So if somebody tries to make you divide by something, you tell them, no, I'm going to multiply by the fraction instead. So if they're telling you to divide by 9, they're really telling you, instead of dividing by 9, why don't you multiply by 1/9 instead? All right, go ahead and pause the video and see how you do on those 3 real quick. All right, so here's your answers. Hopefully you paused the video and tried those. A of t on the first one is we started with 9 and we're multiplying by 3 raised to the t. So the amount we have after a certain amount of time is 9 times 3 raised to the however many weeks or days or years we let go by. Second one is A of t equals 15 times 0.6 raised to the t. This is going to be exponential decay because the 15 is getting smaller. When you multiply it by a number less than 1, smaller than 1, it makes the 15 get smaller. If I multiply by a number bigger than 1, like 3, it makes the 9 get bigger. 9 times 3 is 27. It's getting bigger. That's growth. 15 times 0.6, that's 9. It's getting smaller. That's decay. All right, and the third one, A, in terms of t, is the starting value, 8 times 1/9. They said divide by 9. Don't do that. Write it as multiplication instead. So instead of saying 8 divided by 9, say 8 times 1/9 raised to the t. That's also decay, because if you start with 8 and you multiply it times 1/9, you can do it on your calculator. You get 8/9. That's less than 1, all right? So the 8 is getting much, much, much smaller. All right, now it's nice if this is a whole number or a decimal if you can, but if 1 divided by 9 turns into a messy decimal that goes on forever and ever and ever, don't use that, all right? Because when you use the decimal and it's messy, you have to round it, and that messes up your answer. So looking at 1 divided by 9 on the calculator, it's 0.111111 repeating, all right? I don't want to put that here. I want to just stick with the fraction instead of rounding a decimal. So use the fraction if the decimal turns out like messy. I call it messy if it goes on forever. All right, now we're going to do a couple more word problems, but we're going to change the wording just a little bit. We're going to phrase it in terms of percent increase or percent decrease. So it's still kind of the same problem, same formula, but we have to kind of phrase it a little differently. So recall that 100%, if you change it to a decimal, is 1. All right, you just knock off the percent sign and you move the decimal 2 places to the left, and now you have 1.00, which we just say is 1. All right, so remember, anything multiplied by 100% stays the same. For example, if I say what's 100% of 50, of means times, that's 50 times 100%. Well, 100% when you change it to a decimal is 1. So 50 times 100% is the same thing as 50 times 1, which is the same thing as 50. So if you multiply 50 by 100%, you're right back at 50. Nothing changes. So multiplying anything by 100% stays the same. Remember that. Now anything multiplied by more than 100%, which means more than 1 if you're speaking decimal, this is percent, this is decimal, anything multiplied by more than 1 grows. For example, if I say, what's 110% of 50? Well, that's 50 times 110%, like this. 110%, if I knock off the percent and move the decimal 2 to the left, that's 1.1. So this is 50 times 1.1, which is 55. So we started with 50, and we ended up with 55. It grew. This is growth, all right? Because we took more than 100%. If you multiply it by more than 100%, or you multiply it by more than 1, your initial value gets larger. And then if we throw it in reverse here, anything multiplied by less than 100%, a decimal that's less than 1, well, that's decay. It's getting smaller. For example, what's 80% of 50? Well, that's 50 times 80%, like this. 80%, knock off the percent, move the decimal 2 to the left, that's 0.8. So that's 50 times 0.8, that's 40. So we started with 50, and it decayed to 40 because we took the initial amount, 50, and we multiply it by a number less than 100% or less than 1. 80% is less than 100%. 0.80 is less than 1. That makes my initial value get smaller. All right. So for example, let's do a little vocabulary here. Just think of this like a table here. All right. On the left, I have the growth rate. This is how they're going to give it to you in the problem. They're going to say, hey, you got this investment or whatever, and it's growing at a rate of 7%. And you're trying to figure out, well, what do I multiply my initial value by? That's the growth factor we talked about earlier, that number that we multiply the initial value by. Well, if they tell you it's growing at a rate of 7%, they're saying you need to multiply it by 100% plus 7% more because it's growing. They said it's growing. That means it's going to be more than 100%. How much more? It's going to be 7% more than 100%. Well, 7% more than 100% is 107%. That's 1 plus 0.07. Knock off the percent, move the decimal 2 to the left, that's 0.07. 1 plus 0.07. So what you're going to multiply by, your growth factor, you're going to multiply the initial value by 1.07 if they say it's a 7% growth rate. Maybe they say it grows at a rate of 2%, all right? So it grows at a rate of 2%. It's growing, so I need to multiply by something bigger than 100%, specifically 100% plus another 2%. This is 1, this is 0.02. So I'm going to multiply by 1 plus 0.02, or 1.02. So whatever the initial value is, you're going to multiply that one by 1.02 if it's growing at a rate of 2%. All right, they might say it grew by 35%. Maybe you had a really good investment and it grew by 35%. What does that mean? It means however much you invested, you need to multiply it by 1.35 because it's 100% plus 35%. That's 1 plus 0.35, 1.35. All right, let's talk about decay. Decay kind of goes the other way. Decay is like a bad investment, and maybe you're losing money at a rate of 5%. Decay, it's becoming less. That means I need to multiply by a number that's less than 100% because it's decaying, right? How much less than 100%? 5% less than 100%. So minus means less than. 5% less than 100%, all right? This is 1. This is 0.05. So 1 minus 0.05, like this, which equals out to 0.95. You can look at it this way too. You can say 100% minus 5%, that's 95%. Move the decimal, that's 0.95. If we decay at a rate of 20%, decay means we're going to end up multiplying by a number less than 100%. How much less? 20% less. So 20% less than 100. That's 80%, that's 0.80. You can do it that way. Or you can go ahead and write it out. You can say 100%, that's 1, minus 20%, that's 0.20. 1 minus 0.20 is 0.80. So the number that we're going to multiply the initial value by is 0.80. And then sometimes they get tricky and they say decreased by 1.1%. So that's 100%, take away 1.1%. This is a little tricky. Take off the percent sign, move the decimal 2 to the left, that's 0.011, like this. So be able to change a percent to a decimal. This looks like a decimal, but it's not. It's a percent. Knock off that percent sign, move the decimal 2 to the left. That's 0.011. So 100% is 1. This is 0.011. Subtract them, you get 0.989. So if you're losing value by 1.1%, that means you're going to multiply by 98.9%. All right, so let's try a word problem with that outlook. A quantity Q has an initial value of 11 and grows. I underline grow. That means we're going to multiply by something bigger than 1, and grows at a rate of 7% per year. So you have some kind of investment. Maybe you invested 11 something, $11,000, $11 million, whatever you got. We're going to call it 11. So you invested 11 and it's growing at a rate of 7% per year. That's great. Give an exponential function that describes this. Use t in years as your variable. So it's going to be how much do you have after a certain amount of time goes by. So it's going to be q of t. All right, here's a long way of looking at it, kind of in English. In English, what you end up with, your ending value, is what you started with, your initial value, times your multiplier, whatever you're multiplying it by. Now it's growing, so this number is going to be bigger than 1. And then raised to the t, raised to the number of years you're going to let go by. So it's however much you're investing times how fast it's growing for a certain amount of years. All right. Another way of looking at it is ending value is initial value times 100% and then plus or minus the growth rate. It kind of depends on whether it's growing or decaying. If it's growing, you're going to add the rate. If it's decaying, you're going to subtract the rate. Now this one says it's growing. We underlined it. It's growing at 7%. So it's going to be 100% plus 7%. 1 plus 0.07 raised to the t, and you started with 11. And here it is a little cleaner. All right. So the quantity that you have after a certain amount of time is what you started with times how fast it's growing raised to the number of years you leave it in there to grow. All right. Okay, you guys try this one. All right, a quantity Q has an initial value of 5 and decays. I underline decay now. So remember, when it's decaying, it's becoming less. So you're going to be multiplying by a number less than 1. It decays by 2% per year. Give an exponential function that describes this. Use t in years as your variable. So basically the same problem, but it's decaying. All right. All right, so start off like this. Ending value equals initial value times your growth factor raised to the number of years. And then go ahead and pause the video and just take a shot at it and see how you do. All right, hopefully you paused. Another way of looking at it is what you end up with is what you started with times 100% plus or minus the growth rate. It depends on whether it's growing, that's plus, or decaying, that's minus, raised to the number of years you leave it in there. All right, so our ending value, our quantity in terms of how much time has gone by, is what we started with, 5. That was our initial value of 5, times 100% minus, because it's decaying, it's becoming less. How much less? It's losing 2% a year. So this is a bad investment that's losing 2%. All right, so 100% take away 2%. 1 minus 0.02 is 0.98. So the quantity you have after a certain amount of years is what you started with times 98% raised to the t. It's going to become smaller and smaller and smaller. Every time you multiply 5 times 0.98, it's going to get a little bit smaller, a little bit smaller, a little bit smaller. All right, using the graphing calculator is handy. All right, let me show you how to put this into your graphing calculator. All right, let's grab the calculator here. Let me see if I can get it all in here. So to use the graphing calculator, just to put in this equation up here, 5 times 0.98 to the t, just put it in your y equals button. Now, if you want to see it on the graph, you just need to set your window to something reasonable. Now, your window on your x's, you're just talking about how much time has gone by. So if I say, 50 years have gone by, so from 0 to 50, I want to see how my investment is doing. and then I'm going to do zoom fit. And remember, fit is number 0. And I give it a second. It's thinking up there in the corner. When that thing's moving up there, it's thinking. And you can kind of see that it's becoming worth less and less and less. It's getting lower and lower and lower as time goes by. So this is definitely an exponential decay formula. Now, we're not talking about graphing today, but what I wanted to show you was that lots of your numbers are in your table. Like if you want to know how's my investment doing 10 years down the road, or 20 years down the road, or 30 years down the road, all that's in your table here. So you might want to go to table setup, and let's just start at 0 for now and go by ones. So let's start at 0 and go up by ones. Delta means how big a step do you want to take. I want to go up by ones. And now let's go look at that table. So what this tells us is after 0 years, I had 5. That's my initial value. After 1 year, I had 4.9. After 2 years, I had 4.802, and so on. So as the years go by, over here in the X column, you can see that my initial value of 5 got lower and lower and lower and lower and lower. You can see it's dropping, 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 dropping. All right, how is this handy? Well, if somebody asks you, well, how much did you have, later? If you had 5 to start with, how much did you have 10 years later? They might say, what's Q of 10? Well, Q of 10 is 4.0854. That's how much I had after 10 years went by, or 11, or 12, or 13. You have all the answers over here in the Y column. All right, so let's do a couple more here. All right, so in 1995, there were 56.61 thousand performances. All right, they're performing something. From 1995 to 2007, this number increased. That's growth. That means we're going to multiply by a number bigger than 1 by 10% per year. Let P denote the number of performances in thousands. Let T denote the time. All right, that's usually how they do it. So it's going to be P in terms of T. It's going to be P of T, the number of performances after a certain amount of time has gone by. Now this is important. They said let T be not the year, but the time in years since 1995. That's a trick they use a lot. They don't want you to use 1995 or 1996 or 1997. They don't want to use those years. They want you to say T is how many years since we started measuring, since 1995. Make an exponential model. That just means write a formula for P versus T. That means P of T. So P in terms of T. All right, let's kind of walk through it here. Your ending value is what you started with times your multiplier, whatever your growth factor is, raised to how much time has gone by. Now remember, time is going to be years since 1995. It's not going to be what year it is. Ending value is what you started with times 100% plus or minus your growth rate, plus your growth rate if it's growing, minus your growth rate if it's shrinking or decaying. All right, so the number of performances in terms of how many years have gone by is what I started with, 56.61. That's my initial value. When they started measuring this in 1995, there were 56.61. So that's my initial value times 100%, that's 1, plus the growth rate, because it's growing. It's increasing by 10%. That means it's increasing by 10%. It's growing by 0.10, raised to the t. All right, whatever's in the parentheses over here, that's what your exponent's going to be. So a little neater, written a little neater, the number of performances in terms of how many years have gone by is what you started with times 1.1 for a certain number of years. All right, now continuing the problem, part B, it says how many performances does your model give for 2007? All right, now remember, they don't want you to put 2007 in for T. That's not what they want. They want you to put the years since 1995. That's what T is, all right? So I want the number of performances since 2007, all right? All right, T needs to be not since 2007. I said that wrong. The number of performances in the year 2007, except we're not going to use the year 2007. We're going to use how long has it been since 1995. So let's do a quick calculation there. 2007, that's 12 years after 1995. How did I find that? I just take the year they're talking about minus the starting year. That tells me it's 12 years later. So 12 is what we're going to put in for t. All right. So nice and easy to pop it in for t. So the p of t is, there's your equation, 56.61 times 1.1 to the t. Specifically, if I'm wondering about 12 years later, the year 2007, but I'm not going to use 2007. I'm going to say it's 12 years later. The number of performances 12 years later is what I started with times 1.1 12 times 1.1 to the 12th. You guys, it's real easy to put into your calculator, but I do want to show you that you can also look it up in your table. All right, put in your equation, y equals 56.61 times 1.1 to the x, put that in your y equals button. Go look at your table, scroll down to x equals 12, and the y value will be 177.67. So it's pretty easy just to pop 12 in for t and work it out, but it's also pretty easy to put that equation, put this equation in your y equals and go look at your table. Whatever you think is easier, but this x, y value is in your table as well. Okay, last one. An overweight man loses weight. His starting weight is 240, and he set a target weight of 200, so he wants to lose 40 pounds. Let t be the time in months, and let d be the difference in pounds between his weight at the time t and his goal weight. So this is kind of a hard problem because d stands for the difference between what he weighs and what he wants to weigh. He starts out a difference of 40 pounds. He's 40 pounds overweight. He's 40 pounds more than what he wants to weigh. So D stands for difference. How far overweight is he? What's the difference between these two numbers? So the difference between these two numbers is 40 pounds. That's our starting value. He starts out 40 pounds overweight. All right. So between, each month, the difference D decreases by 5%. Decreases. He's losing weight. This is exponential decay. So I'm going to be multiplying by a number less than 100%. How much less? 5% less than 100%. So my ending value, in this case, my ending difference, that's the difference between what he wants to weigh and what he actually does weigh. My ending difference is the beginning difference times 100% plus or minus. This one's going to be minus because it's decreasing by 5% raised to the time. All right, so the difference in terms of how many months have gone by is what he started with. See, this is where it gets tricky. You want to say he started at 240 pounds, but that's not what goes here because they want the difference between what he weighs and what he wants to weigh. So his initial difference was 40 pounds. He was 40 pounds overweight. Times 100%, that's 1, minus, because we're decreasing. How much are we decreasing? 5%, that's 0.05, raised to the number of months. So here it is all cleaned up. The difference in terms of how many months have gone by is his starting difference of 40 pounds times 0.95, 1 minus 0.05, raised to the t. Remember, this letter in the parentheses is your exponent. All right, let's extend that and ask how long will it be or will it take for his weight to reach 215? Now, before we get into that, think about where you're at. He wants to weigh 200 pounds. He weighs 215. That means he's 15 pounds overweight. So the difference between what he wants to weigh and what he currently weighs is 15. So D is going to be 15. All right, think about the question now. The question says, how long? That's a when question. They're saying, when will he be 15 pounds overweight? Well, when is always your x-axis, your time axis, all right? So they're saying, when will he be 15 overweight? The difference between 215 and 200, difference means minus. The difference between those is 15 pounds. So the question is, when will y be 15? So what x produces a y that's 15? That's what we're looking for. I'm looking for an x that has a y of 15. All right, when is y15. Now specifically using the words in the word problem, I'm saying at what time is the difference 15 pounds? But let's just talk about x and y because that's kind of how we're going to look it up in the calculator. So I'm wondering what x gives us a y of 15. All right, I'm going to show you how I'm going to do it here. There's a couple of ways to do it. One way is just kind of bumble through the table. So I'm going to go to my table and I'm going to find when y is 15. When y is 15. So I'm going to bumble through my table and look for the x that produces a 15. Now this is kind of a long way to do it, but it works. All right, first thing I do is I put my equation in. All right, and let's go ahead and set up our table. Let's start at 0 and go by ones. And now that I'm starting at 0 and going up by ones, let's go look at the table. All right, and what I'm looking for is I want to know when. That's my x column. You know, is it 1 month, 2 months, 3 months, 4 months? I want to know when is he only 15 pounds overweight. So he's still 25 pounds overweight. It's getting lower. And where is that 15? Okay, there we go. So it looks like 15 is in between these two numbers here, 15.094 and 14.339. So I know that it happens sometime after 19 months. At 19 months, he's still slightly over 15 pounds overweight. At 20 months, he's under 15 pounds overweight. So it happens after 19. Well, let's take smaller steps. Over here in the x, instead of going by ones, let's go back to table setup. And we know it happens after 19. So why don't we just start our table at 19? Oops, I messed that up. Let's start our table at 19 and let's take smaller steps. So instead of going 1 at a time, let's go 0.1 at a time. And back to our table. All right, and so again, I'm looking for when does it hit 15? Well, somewhere in between here is 15. That means somewhere in between these two x's is 15. That means it happens after 19.1. 19.2, that's under 15. 19.1, that's over 15. So after 19.1, it hits 15. Let's get a little more exact. Back to table set. I'm at 19.1. And let's take smaller steps. So let's go by 0.01. Back to table. I'm looking for when does it change to 15? Somewhere in between there. I'm getting closer. So somewhere after 19.12. Let's start at 19.12. And let's go by a smaller step, 0.001. Back to our table. And as we take smaller and smaller steps, we finally land right on it. So when is he only 15 pounds overweight? At 19.122 months. So when is he 15 pounds overweight at 19.122 months? Okay, a quicker way, if you're good at it, it's called the crossing graphs method, is to put for your second equation exactly how high you want y to be. All right, y is how high. I want high to be 15. I want y to be 15 steps up in the air. So if I make my second line a horizontal line that's 15 steps up in the air and just see where these two cross, that's a quicker way of getting there. All right, let's set up our window here. Window, let's do something reasonable. Maybe, I don't know how long he's going to be on this diet, maybe 30 months. Let's go 0 to 30 months. Let's pretend we don't know the answer. And let's do zoom fit just to give us a nice picture. And let it think. It's up there thinking. So there's him losing weight, losing weight, losing weight, losing weight, losing weight over a period of 30 months. And there is 15. All right, that's a horizontal line that's 15 steps high. What I'm looking for is where they cross. So I'm going to calculate an intersection. And if you just have two lines on there, you can just hit enter, 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 and it will find the closest intersection. And there it says at 19.12, now that one's going to round up to 2. At 19.122, he hit 15. All right, so he will be 215 or 15 pounds over his goal after 19.122 months. All right, guys, that's it.